Welcome to video 4.5, covering percent composition, empirical formula, and molecular formula. This video is going to help you calculate the percent composition of a chemical compound. Then this video will also show you how to determine the empirical and molecular formula given the percent composition of a chemical compound. So the vocabulary terms here are percent composition, empirical formula, and molecular formula. As we get started talking about percent composition, let's just start off with a very easy question, something that you could probably figure out on your own. If you had a bowl of fruit that contained 2 apples, 5 grapes, and 1 banana, what is the percent by mass of each fruit in that bowl? So below I give you some information. I tell you how much each apple weighs, each grape weighs, and each banana weighs. Using this question and using your intelligence, you could probably answer this question. And this is exactly the same thing we're doing with percent composition. So how would you answer this question? This question, if you want to know percent by mass of each fruit, you probably already figured out you would need to find out the mass of each fruit overall and then divide that by the total mass. So your work would look like this. If each apple would weigh 75 grams, you had 2 apples, that would be 150 grams of apple by mass. If I took the part that I was curious in, the mass of the apple, divided by the total mass of the bowl, I would see that by mass, 54.3% of my fruit bowl is made up of apple. Doing the same amount of calculations for the grape and the bananas, by just taking the part over the whole, the part I'm interested in divided by the whole, you would see that you have 9.1% grape by mass and 36.6% banana by mass. This is exactly the same thing you're doing in chemistry right now. But we call this the percent composition, or you might even hear it by percent composition by mass. So the first thing we're going to look at here when we do this kind of problem is we're just going to find the individual mass of each element in the compound, and you're going to divide that by the total mass, or in other words, the molar mass. So percent composition is simply the percent by mass of each element in a compound. This is a relatively very simple idea and calculation. So again, you're going to take the mass of each element, divide by the mass of the compound, times it by 100, and that will give you the percent composition. Just a quick review, molar mass is when you add up all the atoms of each element in a compound. Here's an example of that. If I have BaF2, the molar mass is 175.33 grams per mole. How do we calculate the molar mass of BaF2? You just simply took the mass of each individual atom and add it together. So again, 1 barium is 137.33. Each fluorine is 19.00. Times that by 2 to get your total of 175.33. So again, this is the molar mass of the compound. These are the individual molar masses of each individual element. So again, here's a practice problem. Find the percent composition of barium fluoride. Well, barium fluoride, the first thing you want to do is you want to calculate the total mass of the compound, or the total molar mass, which I just showed you on the previous screen, is at 175.33 grams per mole. And then to do my equation, I just take the individual mass of each element, divide by the total mass, and then times it by 100 to give me the percent. So here again, down below, you can see the total mass of barium fluoride. Up here, you can see the mass of barium. I divide 137.33, divide by 175.33, times by 100, I get 78.33% barium. Likewise for fluorine, this compound is 21.67% fluorine by mass. So when we talk about percent composition, all it is saying is what percent by mass is barium and what percent by mass is fluorine. This is how you would show your work. These are the answers, but again, it's all by mass. One side note, we are going to go to 2 decimal places on your percents here. Just keep it nice and easy. Don't worry about sig figs in here. So again, I went to 2 decimal places on each of these, and let's just keep that as a general rule of thumb. All right, your turn. Pause the video, try this problem by yourself, and then watch how I show you to do it with my hand. But again, using this information, you should be able to figure it by yourself. Go ahead and pause the video now. No, really, pause the video, take time to practice this, because if you don't start practicing it now, you're going to learn it slowly in class, and the test is less than a week away. So seriously, pause the video and try this now yourself. And after you give it an honest, fair shot, watch how I do it. All right, welcome back to those of you who listen to me and trust my guidance on learning this. The rest of you, okay, here's how it goes. All right, so again, if I want to find the percent composition of propane, basically we're going to find by mass what percent of this is carbon, by mass what percent of this is hydrogen. So the first thing I need to do is I just need to figure out what's my mass of carbon. Well, if carbon weighs 12.01 grams per mole, oh yeah, by the way, how did I get that number? It's right here, and we're going to 2 decimal places like we always do. So on all molar masses in this class, we're just going to go to 2 decimal places. So again, I got carbon's at 12.01 grams. My hydrogen is at 1.01 grams per mole. And then now I need to find the percent by mass. Well, you see how there's 3 carbons? I have to multiply this number by 3 to get my total mass of carbon. I got to multiply this number by 8 to get my total mass of hydrogen. So what that's going to give me, if I put that in my calculator, if I say 12.01 times that by 3, gives me 36.03 grams per mole. And then when I do this, again, I can do it in my head. You can use a calculator if you want, but it's going to be 8.08 moles per gram. Add those 2 together to get your total. And so we see the total mass is going to be 44.11 grams per mole. Individual masses, total mass. But now we have to find the percent composition. So what do? Well, you're going to take that number and you're going to divide it by the total grams per mole. Take this number and divide it by the total of grams per mole. So again, what are we doing? We're just taking the part I'm interested in, which in this case is carbon, divide by the total. Part I'm interested, which is hydrogen, divide by the total. And then of course we have to divide it by, or times it by 100 because it's a percent. And then we just simply do our calculation. 36.03 divided by 44.11 times that by 100. And again, I said go to 2 decimal places. So by percent composition, you have 81.68% carbon. Down here, I got 8.08. Divide that by 44.11. Times that again by 100. Go to 2 decimal places. 18.32% hydrogen. So notice when I go to answer this question, when I go to find the percent composition of propane, it's 81.68% carbon and it's 18.32% hydrogen. 2 decimal places, label it with percent, and label it with the chemical you're talking about. Okay, so that is percent composition. Fair enough. So now from percent composition, we're going to go to a concept called empirical formula. So empirical formula and molecular formula are things you've already been using, but we now just got to kind of learn a little more about the difference between them. So an empirical formula is a chemical formula, but you notice that an empirical formula over here in the chart is when you have the lowest whole number ratio of the compound. So again, my molecular formula might be C6H6. A molecular formula is showing you the actual chemical formula of your compound, but the empirical formula is the term we use when we're talking about the lowest whole number ratio. So again, here's a 6:6 ratio. If I reduce that to the most common terms, it's going to be just a 1:1. This molecular formula is C2H2, but I can reduce it to C1H1. Here, glucose, I got C6H12O6, but that can be reduced again to C1H2O1. And then water is a situation where the molecular formula is also the empirical formula. So as we get started, and as we look at some of these empirical formula problems, the first thing you need to learn is these definitions. Remember, empirical formula is the lowest whole number ratio, and then a molecular formula is the actual formula of that chemical compound you have. Sometimes the empirical formula and the molecular formula are the same, and sometimes they're not. You just got to pay attention to what's going on. So again, here's another example. BH3 cannot be reduced anymore, so that's my empirical formula. However, B2H6 is my molecular formula because that can be reduced. This is the actual molecule we're talking about, and it's also called the molecular formula. So here's a problem. Here's how you would do these problems. So what you're going to do here in a second is I'm going to give you the percent composition. So I'm going to give you these percentages, and you're going to work backwards now to find for me the empirical formula. So here I gave you the chemical, formula. I'm sorry, I gave you the chemical name, and you found out the percent. Now, in a second, I'm going to give you the percent, and you have to work backwards to come up with the empirical formula. So before we do that, there are 3 steps you're going to follow to get the empirical formula. I'm going to show you how to do this. I'm going to let you practice it once, and then we'll be good to go. So again, step 1 on how to go from percent to the empirical formula. First, you're going to convert the percent to mass, which I'll show you. So you're going to assume that if I give you a percent, assume it's out of 100. You're going to convert that from percent to mass, and then from mass to moles. Again, you'll see me work this out here in a second, and it'll all make a lot of sense. The second step is you're going to do what we call normalize the number to 1. You're going to divide each number of the moles by the smallest whole number available. And then step 3, we're going to round those numbers up to a whole number, and those will be our subscripts when it goes to write in our empirical formula. Step 4 is not always necessary, but again, when we go to divide and it doesn't come out to anything close to a whole number, if it's too far away to round it, we're going to have to do another mathematical hurdle. We're going to have to multiply usually by 2 or 3 to get this to be a whole number. And again, I'll show you an example of that down below. It might be helpful to come and relook at these after I show you this first problem. So here's a practice problem. A compound contains 2.016% hydrogen and 32.6% sulfur and 65.3% oxygen. Determine the empirical formula for this compound. So the first step you're going to do is you're going to convert your percent into grams and then convert from grams to moles like we've done all year long. So again, step 1A, you could call it, is take your percent and turn it into grams. Just automatically do this. Take your percent, turn it into grams. Take your percent, turn it into grams. And then step 1B, if you want to think of it that way, turn your grams into moles. Again, where did I get the molar mass from? This came from your periodic table. Same thing here, came from your periodic table. So once I convert from grams to moles, I get these numbers. These are the amount of moles. These are the number of ratios I have in my empirical formula. However, these numbers are not normalized to 1 yet. So the second step we're going to do is we're going to divide it by the lowest number. Again, when I look here, I see I get this 1.016526. I put it in pink. What you're going to do is you're going to take this number and divide it by all the other numbers to just basically normalize it all to 1. So when I normalize these to 1, I see this comes out to 1.964, this comes out to exactly 1, and this comes out to 4.015. What we're going to do then is, because this number is so close to 2, we're just going to round that to 2, and that's our step 3. We're going to keep this at 1, and we're going to round this down to 4. So what that tells me now is that my empirical formula, I have 2 hydrogens, I have 1 sulfur, and I have 4 oxygens. So again, you took the percent and turned it into an empirical formula. Again, review steps 1, 2, 3, and 4 before you try this practice problem. But again, guys, try this yourself. It's going to make your life so much easier if you give it a fair shot, opposed to just watching me do another practice problem. So try it, pause it, and then when you're ready, watch me do it. All right, here we go. So how do I do this one myself? All right, so you are given a sample with a compound that has 43.67% phosphorus, 56.33% oxygen. What are you going to do? Well, we're going to take our 43.67 and we're automatically going to turn that to grams of phosphorus. We're going to take our 56.3 and turn that into grams of oxygen. Now we're going to convert this into moles. How do I do this? Again, I look at my periodic table. I am reminded that phosphorus has 30.97 grams in every 1 mole. So I'm going to go 30.97 grams per mole. Same thing with oxygen. If you check your periodic table, you see there's 16 grams in every mole of oxygen. When I do this and I put that in my calculator, again, 43.67 divided by 30.97, you're going to get 141,007 2.4. Notice how I went out to 6 decimal places here. It's just going to help you keep your answer precise. So I would suggest that when you're doing these kind of problems, keep your math part out to 6. It's ideally if you kept the whole number there, but really keep it out to 6. If you do the next one, that number would come out to 3.520.625 mole of oxygen. All right, so now this is the ratio that you're dealing with. You have 1.410074 phosphorus to every 3.520.625 oxygens. However, I cannot write this down because all chemical formulas need to be in whole numbers. These are not whole numbers. So what we're going to do is going to normalize it by 1. How do I normalize it by 1? I'm going to divide these by the lowest number. Here, that number is 1.410074. Here, 1.010074. That's going to make this come out to 1. And that's going to make that number, if I do it on my calculator, 3.520.625. Divide that by 1.410074. That's going to come out to 2.4967 oxygen. Again, this is the correct ratio. I do have 1 phosphorus for every 2.4967 oxygen. However, can I write this down? Is this an acceptable chemical formula? No, because this is not a whole number. So this is where you would do step 4. If I multiply both of these by 2, that turns these both into whole numbers, and then that gives me my final and true accepted answer, P2O5. So again, I went from percent and found the empirical formula. This is the lowest ratio that this guy can exist. I can't do here because that's not a whole number. I can't do here because it's not a whole number. So we do these mathematical operations to get that to a whole number. Okay. All right. One more thing to show you, and this thing is the easiest of them all. We can now convert between molecular formula and empirical formula. So if you remember from before, molecular formula and empirical formula have the same ratio, just your empirical formula is when it's in the lowest, and your molecular formula can be a higher ratio of whatever compound you're actually talking about. So if you want to convert between molecular formula and empirical formula, all you're going to do is use a simple equation where your x is a whole number. So you can determine the x by taking the molecular mass and divide it by empirical mass. Or once you know what that x is, you can also use it in this formula right here to determine your molecular mass. This is pretty simple. I'll show you a practice problem. I'll let you try it. You're going to pick it up easy. So say you have an empirical formula of P2O5. Determine the molecular formula if the molar mass is 283.99 grams a mole. So what we're saying is I have some unknown molecule that has this mass. I have some unknown molecule that has a molecular formula that I don't know yet that has this mass. Well, if you're given this as the lowest common ratio, if you're given this as the empirical formula, what is my unknown mass? So what you're going to do is you're going to use the equation you just saw on the screen before. But before I do that, I have to determine the empirical molar mass. So basically, if I know how much this weighs, and I know how much my unknown molecular weighs, if I can figure that out, which you can off your periodic table, right? 2 phosphorus, that's the mass. 5 oxygens, that's the mass. So now I know my empirical formula mass. If I divide these two, if I divide my unknown, basically use this equation right here, take the molecular, divide by the empirical, you get this multiplier of 2. So now that I have a multiplier of 2, I am simply going to double up this ratio. I got to keep the 2 to 5 ratio there, but I'm going to double up my subscripts by saying 2 times P2O5, which would give me my final unknown molecule of P4 oxygen 10. Pause the video, try it yourself. Okay, so determine the chemical formula of a compound with the empirical formula CH, molar mass of 78.100 grams. So the first step you're going to do, if you recall from before, is you want to find out what's the mass of your empirical formula. Well, if I have a CH here, we know every carbon weighs 12.01 grams per mole, and we know every hydrogen is 1.01 grams per mole, right? So then what I want to do is I am going to add that together to get my 13.01 grams per mole, and that's going to be called my empirical formula. I'm going to label that EF. So now I have some molecular formula that is labeled as, that has the mass of 78.110 moles. So how do I know how much to multiply this by? We're simply going to divide that. If I divide 78.11 divided by 13.01, what's that come out to? That's going to give me my multiplier. I take 78.11, divide that by 13.01, and it gives me this multiplier of 6. So now what I'm going to do is I'm going to take 6 times that empirical formula, and it's going to give me my new molecular formula right here. Hardest part about this is understanding the definition of an empirical formula. You just got to remember that's the lowest whole number ratio. And then understand that the molecular formula is your actual molecule. Sometimes your empirical formula can be a molecular formula. Sometimes it's different. To figure them out, all you do is divide their masses, get the multiplier, and figure out how many times you multiply that by. We'll practice this in class again. I'm sure some of you guys might have some questions about this, but that's this video. So again, long story short, we can use these simple mathematical formulas to determine percent composition, empirical and molecular formulas. I hope you have a great day.